Alright, so in this video lecture we are going to be looking at analytical synthesis and really just starting to set up the problem so that we can look at loop equations, vector loop equations, and then use those to talk about how do we synthesize a variety of tasks, motion, path, and function, and then getting to actually doing a synthesis of a 2-precision position motion generator. So let me start off by talking about how do we set up our vector loop equations. So starting off, I've just got a 4-bar here. And this 4-bar has 1 precision position, but imagine that I might have 2 or 3 or 4. I can have multiple precision positions, so I can move this from position 1 to perhaps position 2 here. Now, what I'm going to do is try to represent the links of this vector with, the links of this 4-bar with vectors. So it's going to look something like this, where I'm going from this ground pivot right here. Let's see if I can get my pen to work. And go up to this moving pivot right here, and I'm going to call that my W vector. I then am going to go from that moving pivot up to the precision point, and I'll call that the Z vector. I then am going to connect my 2 precision points with a displacement vector that I call my delta vector, Greek delta, and I'll call it delta 2 in this case, going from position 1 to position 2. And then to close my vector loop, I simply have the W vector in its rotated form, so I'll call that W prime for now, and then I've got Z, and this is Z prime. So I'm going to have W rotating by some angle. Often we call the W rotation beta. And so just like we had talked about before where I can have rotations of these vectors, I can now say that W prime is equal to W times the rotation operator e to the I beta. And let me make this beta 2 going from position 1 to position 2. So this is how we can use this polar notation to jump from one vector to a rotated vector. Now what I'm going to do is just represent this one side of the mechanism and recognize that I could treat the other side of the mechanism, the W star and the Z star, in the same way, and we'll treat the other side in just a moment. So here is that left side of the mechanism that I've already sketched out, but now I have just the individual components that we're going to be worrying about here. You'll also notice that in addition to the beta 2 angle that I have for the rotation of the W vector, I also have a rotation alpha 2. This is how much the coupler rotates. And the way I'm measuring this is I'm saying, let me take Z in its initial position, redraw that over here as being parallel to the initial Z, and then I'm measuring alpha from that. So that's what that alpha 2 measurement is. We always reference back to the first position whenever we're doing all of these. So here I have only positions 1 and 2, but if I had third position, I'd always be measuring back to the first position as well. Now, let me use this to start to formulate what we call our standard form equation. So our standard form equation, what we're going to do is we are going to go up the left side of my mechanism first, the displaced side, if you will. So I can add up these vectors and I can say I've got W e to the I beta 2, and then I've got Z e to the I alpha 2. Then I'm going to go backwards down the delta vector, so I'm going to subtract off the delta vector, minus delta 2 in this case. And then I'm going to go backwards down the Z vector and the W vector, taking me back to ground, therefore 0 when I add up all these vectors. So I can add on to this Z, and then add to it W, and then this is all equal to 0. So now I've got a vector loop equation, all equal to 0. I could rearrange this and basically collect my terms, my W's and my Z's, and these rotation operator terms. So this collected form, I've got W times, in parentheses, the rotation operator e to the I beta 2, and then I'm subtracting off the other W that I had. I'm sorry, the one piece I missed here. Both the Z and the W, these should have been subtracted from this equation up here, so let me change this in the notation. So I apologize for that. Let me subtract off Z and W. So I got minus Z minus W because I'm coming from tip to tail. So I've got e to the I beta 2 minus 1, and then I'm adding to this Z times its rotation operator e to the I alpha 2 minus 1, and then I throw the delta vector over to the other side of the equation, and I get delta 2. This is now what we refer to as our standard form equation whenever we're doing synthesis. And we're going to use this over and over again, whether or not we're doing 2, 3, 4 precision positions, motion, path, or function. We're going to use this standard form equation over and over. So this is now, let me jump to the next screen here. Now this standard form equation is for the left side of our mechanism, the W and the Z side. Now I can do the exact same formulation for the W star and Z star, recognizing that my W star vector is going to be rotating by a different angle, gamma in this case. Z vector, well, the entire coupler is rotating by the same angle. So Z and Z star both rotate by alpha. So as I reformulate this standard form equation for the second position, or I'm sorry, the second dyad, the W star and the Z star, I have then what you see on the lower right. You'll notice in both of these cases, now I'm talking about the jth position. So previously we were going to position 2. Now I'm going to position j. So this is a little bit more generic, so I could go to the second position or the third position. But regardless, I'm always measuring this back to the first precision position or the first W vector or the Z vector. All of these measurements go back to the first position. So we normally now focus on just one side of this mechanism and then repeat the exact same thing for the second side for the W star and the Z star. All right, now let's talk about how do we use these vector loop equations and what is actually prescribed as part of the problem when we have different tasks. So I've got the same mechanism up here, and now I'm looking at motion, path, and function. Now remember motion generation, we're thinking about a coupler moving in space, and not only its location, but also its orientation. So what is prescribed, meaning what comes as part of the problem statement for a motion generator, are the displacement vectors, the delta vectors, and here I say delta is because I got to have position 1 to 2, 1 to 3, 1 to 4, as well as the rotation of the coupler represented by alpha. Now, when I go to a path generator with prescribed timing, remember path, I'm only looking at a point moving in space, so I have a displacement vector describing that displacement, or a delta vector, and then I also have prescribed timing, which is the rotation of the input link. In this case, that would be the beta angle. So when I go to a path with prescribed timing, what is prescribed here are the delta angles, the delta vectors as well as the beta angles. Finally, a function generator. This coordinates the rotation of an input link with the rotation of an output link. In this case, the input is the W vector, the output is the W star, and so the rotations of those two are beta and gamma here, and so those are my prescribed variables, and that means what is coming as part of the problem statement. So with all that said, let me take a step back now to motion generation, and I'm going to look at the simplest version, which is a 2 precision position problem. So here's my 2 precision position motion generation. I've got my standard form equation right here, and again, this is the way we formulated this is we went up the displaced side of the mechanism, and then we came back down the undisplaced side of the mechanism and put these together, collected our W and our Z terms. And now I start to say, well, what are my knowns and what are my unknowns in this equation? Now my knowns are, again, being prescribed as part of motion generation. I have the displacement vectors, or the displacement vector, singular in this case. I've got delta 2. It has x and y components, so it can count as 2 scalar components. My other known here is the rotation of the z vector. So I've got alpha right here, prescribed as part of the problem statement. So I've got the alpha also. Now my unknowns in this case. The unknowns are really everything else that's in that vector loop equation. I've got the W vector, which again is a vector, therefore it has 2 components. I've got the Z vector, which also has 2 scalar components. And I have the rotation of my input link, the rotation of beta. So in this case, beta 2. So when I add these up and say how many scalars is that, well, W is 2 scalars, x and y components, or magnitude and angle. Same thing for Z, so I've got 4 between those 2 vectors. And then I've got a beta rotation, so I've got a total of 5 unknowns. And then I say, how many scalar equations do I have? Well, I've got this single vector loop equation. The vector loop equation has both x and y components to it, or real and imaginary if I want to think about it that way. So I have a total of 2 equations. So if I subtract 5 minus 2, I end up with 3 free choices that I need to make. In other words, my system of equations, I simply do not have enough unknowns to meet the number of, or I have too many unknowns for the number of equations that I have. Therefore, I have to make free choices to be able to solve this. So what I'm going to do? Well, I now need to pick something and make some free choices to solve this 2 precision position motion problem. What I'm going to pick is, first of all, very similar to what we did in our graphical synthesis. I'm first of all going to pick my z vector, and by picking my z vector, it is basically saying where is that moving pivot located? Because I know my precision position, and if I pick z, it is now locating that moving pivot. That's the same thing that we did in graphical synthesis, where we picked the location of that moving pivot and then synthesized from there. The other thing I'm going to pick, just to make my system of equations easy, if I pick the z right here, I know my delta as well as knowing my alpha. If I also pick the beta 2 angle, now the only unknown is w, and it's quite easy to solve this equation. So I'm going to go ahead and pick the beta 2 angle, and now I will just solve for w, And as I do so, I just simply rearrange that equation that I have on top, and I get my delta 2. I subtract the z times its rotation operator, e to the I alpha 2 minus 1, and then what's in parentheses multiplied by w I bring into the denominator, e to the I beta 2 minus 1. We know everything then on the right side of this equation. It's either prescribed or is a free choice. And then I can solve for w, and then I have a solution dyad. I could repeat this same thing for the other side of my mechanism, the w star and the z star. I put those two dyads together, and now I have a 4-bar that moves through my 2 precision positions, and I have completed my synthesis. So again, quite simple when we look at it from this perspective. All of this can be plugged straight into MATLAB or something like that, and we will do that in class.